the one we did, and I think I've since removed it from here, but on Friday we started one with, I forget the total context, but we had to, if you remember, we had to change, because I cut it out and it was a sample of 20. In order to do what we needed to do with it, it needed to be a sample of 30, so we augmented that. And then the problem did not state that the population standard deviation was known. It just called it the standard deviation. Right now, when we do these problems, we need the population standard deviation to be known, and we need the sample size. If we don't know that the population is normally distributed, we need the sample size to be bigger than or equal to 30. All right, so with what we're doing here, if you remember back to chapter 8, when we were looking at this flow chart here to decide which distribution to use on a confidence interval, it is the same flow chart to decide which hypothesis test to use, okay? So here we're talking about means. All right, do we have n to be greater or equal to 30? We'll ask that question, okay? If not, they have to tell us the population is normally distributed, okay? But regardless, okay, n being greater or equal to 30 or being told the population is normally distributed, those two things obviously guarantee normality then, okay? This because of the central limit theorem, this because they're telling you, okay? And then as we answer yes to that, the next question is right here and right there, do you know the population standard deviation? Well, if we do know the population standard deviation, then we can use what we call the Z distribution, or in this case, because it's hypothesis testing, we'll use the Z test. Okay. If we did not know the population standard deviation, which is going to be section 9.4, we'll use our T distribution, okay, and use a T test. Okay. So all these examples that we see in front of us should have a statement that says the population standard deviation is, and they should either tell us that things are normally distributed, the population is normally distributed, or we have a sample large enough that it breaks that 30 threshold, and we can assume normality then. Okay, so that's the situation in all of these. So we're going to run through ultimately the 4 or 5 steps that we need to do in all hypothesis testing. Okay. Get everything fixed here. All right, there we go. So the first thing you're going to do is you're going to write down what your null and alternative hypotheses are. Okay. So we're going to say H sub 0 and H sub A. Okay. Now, and I'm going to approach this like we have other types of tests at our disposal right now. Obviously, we don't. But we're going to read these through and kind of talk about what is the parameter, what is the quantity from the population that we are trying to test here. It says it has been reported that the average credit card debt, okay? So we're looking at an average, correct? And we talk about averages, that's a mean, so we're talking about the population mean mu, okay? Down the road, once we get into 3, 4 more sections, we will have to decide, do we put mu here, or do we put sigma? Do we put sigma squared? Do we put p? Okay? We'll have to make all those decisions. And it's based off of phrases like the average. Okay? If it said it has been reported that the proportion, okay, then we'll use p. Does that make sense? Okay, so we have to be able to decipher what parameter we're trying to test. So we're using mu here. Says it has been reported that the average credit card debt for college seniors is $32.62. The student senate at a large university feels that the seniors have a debt much less than this, so it concludes that a study of 50 randomly selected seniors and finds that the average debt is $29.95. Population standard deviation is $1,100, with alpha being 0.05. Is the student senate correct? Okay. So what we're going to do here is we're going to determine what is the current accepted average in this problem. What are they telling us that we are assuming to be the average for college seniors? 3262. Okay? So that is our null hypothesis. Remember, that's always what the accepted value is. Okay? In this case, the accepted mean. Okay? What is the student senate arguing here? What is their claim? That it's below that. Okay? So it's saying it has a debt much less than this. So we would say less than 3262. Is that okay with everybody? Now, we talked about this previously. When we look at our hypotheses, they should be complements of one another. And right now, they're really not. Okay? Only way that they could be complements of one another is if this one becomes greater than or equal to, right? Okay? Which is fine. That makes them true complements, but it's not a necessary thing in hypothesis testing that we do that. Okay? What we're going to find out is that we just want to make sure that when we go through our testing, that we're not right on 3262. Okay, so if you want to put greater than or equal to here, that's fine. But because, like if you were in Math Excel or something like that, choosing, because they give you like 4 options for hypothesis tests, and you click the right bubble, this would be the bubble that you would be clicking from this, because it says is 3262, and that does not say is more than 3262. Does that make sense? Some textbooks, some researchers will say that they always use equality here, and then less than or greater than down here, or not equal to. Okay, so which one of these is the claim? It's the second one, because if we look at this, it says the student senate at a large university feels, believes, reports, claims. Those are all analogous phrases. Okay, so it's going to put the claim right here. Okay, is that all right? All right, so now what we want to do is we want to attach a z-score to the sample data. Okay, so the sample data came from these 50 people and provided all of that information. Does that make sense? Okay. We also want to talk about alpha being 0.05. So there's really 2 steps here. You're gonna find the z-score of the sample data, and you're going to find the z-scores that attach to an alpha of 0.05. And the order that you do those is independent. Doesn't matter what order you do. Okay, I think most people prefer to kind of deal with the alpha equals 0.05 first. Okay, so let's do that. In order to determine, basically what this alpha is telling me, that's the probability of us rejecting a null hypothesis that should have been accepted or should have not been rejected. Does that make sense? Okay, it's the probability of type 1 error. Okay, and it's attached to the alternative hypothesis. Okay, so the alternative hypothesis is it a left tail, right tail, or two-tail test? Anybody remember? It's left tail, and if you can't remember that, as long as mu is first, if you think about the inequality sign as being an arrow, it's pointing to the direction that the tail needs to be in. Okay, so it's a left tail test. So what I'm going to do is I'm going to draw my picture, because my picture is going to be my device or my tool that I use to make my decisions on the null hypothesis. So I'm just going to draw in a left tail area. It doesn't have to be to scale or anything like that. But that left tail area there is going to represent alpha to be 0.05. That's 5% of all of the area underneath the curve. Okay? We need to determine what is that z-score. Let's say z sub alpha right now. What is the z-score that goes with that that establishes that 0.05 area. Okay. Now, if you rummage through your notes from last week, I gave you some common values that you can use. Okay. So here we got left-tailed. Alpha was 0.05. Those are the most common alphas that we use, and it's negative 1.65. Okay. I'll show you how to do that with your calculator as well. So Z is negative 1.65. If we're using Desmos, or not Desmos, sorry. Desmos is a pain in the butt. I'm not even going to entertain using Desmos. Use Excel. All right, so in Excel, what we're going to type in is equals norm.inv. Okay, we're going to type in the probability, which is going to be the alpha, 0.05. And then the mean is 0, standard deviation is 1. That's what you always got to type in there. This will always, 0 and 1 will always be constant. 0.05 is going to be your left cumulative area. Okay, so hit enter. You see that it still gives you the negative 1.6. Now, because the table uses a different, this is just more accurate, negative 1.64, a little bit more accurate than what the table was giving me, negative 1.65. Doesn't matter though. Okay, we'll be okay. Is that all right? So that's where that value there comes from. Now, what we are going to do next, okay, and I'm just going to draw real quick right here that our null hypothesis is we're saying that is the mean. And the mean, if you remember the normal distribution, is in the middle, right? Okay. So what we're basically doing here, and what this image is showing us, is that if we find out that our sample data, when we standardize it as a z-score, if that sample data falls in the red, we're saying that it was far enough away from center here, okay, that difference was so big that it could not have been due to chance. It could not have been due to maybe a bad sample or just maybe a uncharacteristic sample of the population. Okay, so we are going to see if our z-score of our sample data, the stuff we have here in yellow, where it falls. Does it fall in the red? Because then we can say, well, if it falls in the red, then this must not have been the true mean of the population. If it falls in the white, we're saying, yeah, it's different, but it's not different enough for us to argue that the mean is not 3262. Does that make sense? Okay. So in order to do that, we just got to run through our z-score. Okay. So we're going to find, and a lot of times you'll see them write like z and then a subscript of data here. And it just allows you to distinguish what z-scores were what. Obviously, we got the one here with alpha, we got the one with data. So if you remember, okay, that is x bar minus mu, and we divide it by standard deviation. But because this is a sample mean, we're going to divide by the standard deviation of the sample means, which we refer to as standard error. Okay, so there's two ways you're going to see this written. Sometimes you might see it written this way: standard deviation of the sample means, okay, which is the same thing as x bar minus mu over sigma divided by square root of n. Okay. As we work through, I'll probably use this one. I think it's just more direct when we're plugging things in from the given information. So our sample had a mean of 29.95. Okay. Mu, and here is why our null hypothesis has equality in it. Mu is 3262, right? So that's what's going to go right here, 3262. Standard deviation of the population, $1,100. Divided then by the square root of n. N was 50 people. Okay. So we've been doing that. Okay. If you recall, we did z-scores back in chapter 1. Okay. And we've been doing it progressively through the entire course. So my hopes are that that's not something that is going to be extremely complex for us to figure out. So we're going to go 2,995 minus 32.62. Okay, then we'll divide that by 1,100 over square root of 50. And we get our z-score to be negative 1.72. Negative 1.72. Is it okay? Negative 1.72. Okay. So now we go find where that is located on this. On negative 1.72. Would you say, is it to the right or to the left of this mark right here? It's to the left. So negative 1.72, z of your data equals negative 1.72, would be about right there, correct? So what region does that fall in? What do we call that red region? It's the negative 1.65 is the critical value. So then the red region is called the critical region, right? Okay. And we call it a critical region because that's where it tells you to reject the null hypothesis. Okay. So we reject, so what we're saying is that we have data that says reject the null hypothesis. Which, if we reject the null hypothesis, that tells us that the population average is not 3262. There is evidence to support the claim that the population average is less than 3262. Okay, it doesn't tell me exactly what it is, right? It just tells me that it's not 3262, or we have sufficient evidence to say it's not. Okay, and we're basically saying that we're now, because we just rejected a null hypothesis, right? And we had a type 1 error that was 5%, which essentially says that you rejected a null hypothesis that should have been really, in actuality, accepted. Okay? So we're ultimately saying with that final statement, we're 95% confident that is accurate. Okay? Could be wrong. Could be 5% wrong. Okay? Or 5% probability that we're wrong. Because we don't have the whole population, so we can't make any certainties, but that's the argument. Does that kind of make sense? Now, negative 1.71 or negative 1.72, is that pretty close to negative 1.65? So these two values were pretty close to one another, right? That will be something that we kind of discussed later on, that, yeah, we've got evidence to reject the null hypothesis, but how strong is that evidence? Because they're pretty close, right? Like if my z for my data was like -3, -3 is pretty far from negative 1.65, right? And that would be really strong evidence against rejecting the null hypothesis. So we'll talk about that strength of evidence as we move on. But remember, kind of think about what we're talking about here. these Z-scores, that's standard deviations away from the mean, right? So basically what we're trying to determine is our sample data, is it more than 1.65 standard deviations away? If it's more than 1.65 standard deviations away, it ends up, remember the empirical rule and all that kind of stuff with 68, 95, 99.7, all those percentages, it ends up being far away from the average of the mean, that it's essentially unlikely to happen. Okay? Therefore, that's why we were rejecting this null hypothesis. Does that make sense? All right, so we'll jump down here to this. Let's see here. All right, let's do this one here. Heights of 1-year-olds. We got these heights of 1-year-olds. It says the average 1-year-old is 29 inches tall. Okay. When you guys go to, when you have your own 1-year-olds, you'll go to like yearly, monthly checkups, that kind of stuff, and they'll measure them, they'll weigh them, they'll measure like head circumference, length, weight, all that kind of stuff, and then they'll put you on a chart, a projection chart, and compare you to the percentiles of all 1-year-olds or all 6-month-olds or whatever. So this is, I mean, you'll interact with this at some point in your life. There's a random sample of 31-year-olds in a large daycare franchise resulted in the following heights. Alpha being 0.05, it can be concluded that the average height can it be concluded that the average height differs from 29 inches. Okay, so as we read this, okay, we're still talking about averages. So our null hypothesis and alternative hypothesis are going to deal with mu. Okay, and right now, which one, okay, or which value in here is the accepted average for 1-year-olds? .29 inches. As we read that, mu is 29 inches. Okay. Now the question, as we read it, says, can it be concluded that the average height differs from 29 inches? When it says differs, does it tell me a direction of differing? No. Okay. So when it does not tell me a direction, we just have to make sure it's not 29. Okay. Now, in the phrasing of these, and I think these are the ones that people struggle with the most in terms of which one's to claim and which one's not to claim. Because it never says that like a reporter reports or an employee thinks or somebody believes or feels, something like that, right? Okay. When at the end, though, if it ever says, can it be concluded that the average height differs? Okay, so this really, that wording right there tells me that this is the claim. Okay, so as you read through a problem and you can't figure out, doesn't use the word claim, doesn't use the word feels, believes, reports, but it says can it be concluded, then they're assuming that the alternative hypothesis is the claim. Okay, so now it's 5% again. Okay, alpha is 5%. But it's a different type of test, right? It is now a two-tailed test because of this unequalness here. Okay? So if it's a two-tailed test, then we are finding an area to the right and to the left. Okay? Our null hypothesis is still there in the center. Now, these red areas, then, these rejection areas, need to total 5%. So that one will be 0.025. Does that make sense? They've got to be symmetric. They have to be equal in size. So in order to find the Z-score attached with alpha over 2 in this case, I'm going to, on Excel, type in norm.inv 0.025. And you get negative 1.96. And that's also in your notes if you would search back a few pages. So That's a z-score of negative 1.96. So what is this z-score over here? Positive 1.96. Good. Okay, so that we've now developed our tool to decide whether to reject or fail to reject. Now we've got to run through the data. And what kind of stinks here is that the data is not processed. So if I want to go the z-score of the data, okay, remember it's x bar minus mu over sigma divided by root n, right? Okay. Now, as I go through this, I'm going to fill in the things that I know. Mu is negative 29, or minus 29 in this case. Sigma, they tell us, is 2.61. And we have 30 children, 31-year-olds. What don't I know? I don't know the mean. Okay? So that's what they're giving me with that information. I'm going to kind of cheat here real quick. Think I can. No, I can't. Thanks. I was hoping I had it typed in as a table and I could just cut and paste it. But so I'll type these in real quick. 25, 30, 29. All right, so I typed all those in. Okay. I'm just going to type in now equals average A 29.45. 29.45. So just remember that the way that they can present you with information, you might have to do a little bit of the processing yourself. Okay, especially when we get into t-scores eventually. They're probably not going to give you the sample standard deviation. You would actually have to come up with that on your own as well. So now we calculate that. So up here, just change this 29.45. This number was 29. 2.61 was sigma. And we had 30 individuals. So 0.94, right? So 0.94 would reside maybe about right there, right? So is that in the rejection or non-rejection region? Non-rejection, okay? So we would write that we have evidence that would allow us to make the conclusion not to reject the null hypothesis. Okay, and if we do not reject the null hypothesis, then we do not have evidence to support the claim that the mean height of 1-year-olds is different than 29 inches. Okay, does that make sense? Even though that sample of 30 people shows us that we do have a height greater than 29 inches in that sample, but it's not big enough to say that the mean height of the population is different than 29. There is an assignment 9.3. You can start in Math Excel. I think it's got 6 or 7 questions on it, something like that. And that'll be open until Wednesday.